Basically, we're using the tower as our cooling source for the building, not just the condenser water for the chiller, but as for the building itself. To accomplish this, we need really low wet bulb conditions. I'm not even going to say necessarily ambient conditions, because in some regions you can actually achieve really low wet bulbs even though we may have a decent dry bulb temperature. Essentially, what we end up doing, we're going to process the condenser water through this heat exchanger. And what we'll have is a plated heat exchanger inside of the central plant. And that heat exchanger will process the chill water loop and the condenser water loop through it. Now, under normal mechanical cooling, so we're going through the chillers, but we wouldn't utilize this heat exchanger. It would have bypasses installed usually that will completely divert around it and won't even process through it. In those situations, we don't want it to. But when we go into economizer mode, well, then we will actually divert to bypass the chiller typically, and then the condenser water will flow through one side of the heat exchanger and the chill water loop through the other side. Once the plant switches modes, the condenser water set point will be lowered to around, say, 40, 45 degrees. And we need to be able to hit those lower end metrics with the tower given our wet bulb temperatures. We have to take in tower approach, things like that, in order to achieve that. And quite literally, our cooling tower becomes the cooling source for the building at that point. So we're using the condenser water through the cooling tower to chill our chill water loop. Now, in some cases, when the plant will transition into economize mode, the plants I've worked in will also raise the chill water set point a bit. So instead of running a 44, 45 degree set point, they may increase to a 48 or 50 degree. And it just depends on the building and what its humidity load is like, which in these cases, typically our humidity is down, right? So in the fact that we have a low enough wet bulb in the first place, we typically have a much lower humidity to begin with in this situation. Running a higher chill water temperature is not that big a deal because we're not worried as much about dehumidification. It's just about processing some general level of sensible load. That's really our only focus. So at that point, we completely remove the mechanical load from the electrical system to cool that entire chill water loop. And the cooling tower, if it's big enough to handle it, will be able to sufficiently keep that chill water loop processed on its own. And that is the whole concept, is the cooling tower then cools the condenser water down cold enough to then, through a plated heat exchanger, chill the chill water loop. And the chill water loop will still function the same. It's just going through the heat exchanger, the plated heat exchanger, which we call the economizer, instead of going through the chiller itself. And that is the main separation there. And again, there's going to be bypass valves that divert flow and do this appropriately so that we don't, when we're in mechanical cooling, we don't want to use the economizer, and vice versa with the other way around. And this will be something that some plants will have an automatic changeover where there's set parameters, and it's maybe doing some kind of load calculation on the building and the air handlers or whatever the load is at the time, and what the outdoor humidity and wet bulb temperatures are. And then once we cross this threshold for 30 minutes, X amount of time, whatever it is, it will go into an automatic economize mode, and everything will adjust and tune itself accordingly. There's a lot of plants that they'll do this manually, to where they'll monitor it. And when they get into, say, the cooler season where it's more shoulder weather, they can manually go in and toggle something in the automation system, and everything will kick over into a economize mode. And it is significantly more efficient because at that point we're still running the cooling tower and the fan. This only works if the wet bulb temperature is low enough. So if it's not low enough, there's no point, because we can only cool via evaporation in the tower as cold as our wet bulb temperature is. At that point, we're strictly we have the load of the cooling tower fan and the pumps to cool the space without having to run whatever the load is through the chillers at the time. And at that point, while chillers have gotten a lot better about running at much lower part load conditions, they still tend to struggle. A YK be an easy example to throw under the bus. If flow is not just right and you're not keeping the condenser water low enough, you get into those part load conditions that YK is going to surge or going to struggle with surging far more. Where in this case, you kick that over to the economizer instead and just shut that YK completely off. Well, now all of that struggle that a YK may have at part load conditions just gets pushed off onto the cooling tower, which typically isn't that big a deal. So that's where it is more efficient. We just use far less energy in total. And that's how it can be used in conjunction with a chiller system. I do want to point out these systems do get implemented beyond just chiller context. If you're familiar with self-contains, there are self-contains on the market that have economizer coils that are in front of the evaporator coil. So when you're actually looking through the filter deck, the coil you're seeing is your economizer and your evaporator coils behind that. So those types of systems will also use a economizing mode where if the same conditions, wet bulb gets low enough, conditions are just right, instead of trying to run the self-contained system with usually scroll compressors at really low part load conditions and kill a bunch of energy with compressors throughout the building trying to stage at that, instead we can just cool that condenser water down, route it through the economizer, tell the compressors and the cooling inside of the self-contains to just turn off entirely, and then we can process the building load just through that what was condenser water for the self-contained is now functioning as economizer water flowing through that economizer coil. But again, when we're not in economize mode, we're going to isolate that coil and only flow through the self-contained water-cooled condensers at that point. So this gets applied outside of chillers, and that's just another way this same type of technology can be applied that's not a water-cooled chiller system. One of the things that we really have to be careful with when we're doing this setup is we are intentionally inverting our loop. And this should play a factor in deciding whether or not to go into economize, because this depends on the chiller we have. There are some chillers, or a lot of chillers, who do not overcome an inverted loop on their own very well at all, if at all. There again, there are other chillers who can overcome an inverted loop quite easily. So getting into loop inversion territory is the danger of using a water side economizer, because if at some point we have to transition from economize on the plant level, okay, from economize to mechanical again, mechanical cooling, meaning we're turning the compressors back on, then we've really got to be able to overcome that, because one or two things can happen. If we can't get that condenser water temperature back up and get out of an inversion quick enough, we could either cause a severe migration with the oil into the evaporator, because that's part of what will happen. We'll just very quickly and rapidly migrate that oil over, and then we'll start tripping out on oil pressure, oil alarms, oil loss, things like that. So that'll be one of the symptoms of having a hard time making that inversion transition. Another one would be, and this was something Turbo Cores give me all kinds of fits on. With the Turbo Core, they need the pressure differential for cooling, because their standard package is they do not come with a liquid cooling pump to pump the liquid refrigerant from the condenser through the compressor. So if you don't have that and you're relying on the pressure differentials, well, when you're inverted, you can't feed enough refrigerant into that compressor to keep it cooled, and it will end up overheating on the inverter temperature because of it. Like, you can eventually overcome that, but it's kind of a pain, and you have to go in and do a bunch of manual overrides, especially with the time delays that you should run on those turbo cores. Take the inversion piece of it into account. If you're not expecting that, or you've got chillers that can just take that on the fly and it's no big deal, then you've got a lot more flexibility. But if you've got a situation where you know that you're only going to be in part load part of the day, and you're going to need to stage on the mechanical later in that day, well, you probably don't want to go into economize in that situation, especially if the team on site monitoring those chillers are not trained on what to do if the chiller has a hard time overcoming an inversion. Which, just to clarify, an inversion is your condenser water temperature is equal to, or in many cases colder than, your chill water temperature. So especially the colder than part, meaning they're backwards in terms of which one is hotter than the other. So having to overcome that becomes a major issue. Inversion goes far beyond just having cold condenser water. You could also have hot chill water too, but either way, that's the big caveat you got to be careful with. It can't be just a willy-nilly back and forth process, because that's actually, that you'll lose a lot of efficiency there, and it takes a lot for a chiller to correct that inversion. I'm a fan of it personally. When it's used correctly, when it's applied correctly, is an amazing tool to have in a plant.